Friends, welcome to my YouTube channel. Dhanesh here. In this video, I am going to discuss about BERT, that is bidirectional encoder representation from transformers and its implementation. This is the third video on transformers. We discussed in detail about the transformer architecture and the attention mechanism and how it is different from recurrent neural networks and LSTMs. What is the differentiating factor from RNN and LSTMs in the case of in the case of transformers? Those aspects we discussed in the previous videos. Let's continue. This is the transformer architecture. This is the encoder and this is the decoder. This transformer architecture, if you want more clarity, you can watch the previous videos. In this video, my focus is on BERT. So just I am telling, in this transformer architecture, if you see whether it is an encoder or a decoder, it's a combination of the multi-head attention and a feed-forward network along with softmax activation function. This is what it usually contains in whether it's an encoder or decoder. Fine. Now, see here, we use in the implementation, we are using PYTORCH transformers. So PYTORCH transformers is a library of pre-trained models for natural language processing. To install PYTORCH transformers, you can give a pip install to get PYTORCH. You will give a pip install PYTORCH, then you will get these libraries. See, different models are available based on transformers for NLP, natural language processing. They are BERT, that is the one we are going to discuss, that is bidirectional transformers for language understanding. Then the GPT from OpenAI, GPT-2 from OpenAI, Transformer XL, XLNet, XLM from Facebook are the important models for NLP tasks. See, to install PYTORCH transformer, this is the command, pip install PYTORCH transformers will work. See, bidirectional encoder representation from transformers, or BERT, means the BERT framework, a new language representation model from Google AI, use pre-training and fine-tuning to create state-of-the-art models for a wide range of tasks. These tasks include question answering system, sentiment analysis, and a language reference and a language inference. Fine. BERT architecture, if you see the BERT architecture, BERT uses a multi-layer bidirectional transformer encoder, multi-layer bidirectional transformer encoder. Its self-attention layer performs self-attention in both directions. This is the difference. Its self-attention is there in both directions. BERT uses bidirectionality by pre-training on a couple of tasks. Master language model, that's the one, and the next sentence prediction. These two are the important principles that differentiate from the transformer. BERT handles the masked language model and next sentence prediction. See, BERT architecture builds on top of transformers. We have currently two variants are available. BERT base, that is 12 layers transformer blocks with 12 attention heads and 110 million parameters. BERT large, that is 24 layers transformer blocks, 16 attention heads and 340 million parameters. These are all the two models available. Now this is the BERT architecture. This is the base and this is the BERT large. Fine. Now, text pre-processing. See, the developers behind BERT have added a specific set of rules to represent the input text for the model. Many of these are creative design choices that makes the model even better. There are three combinations of embeddings, that is the position embedding, segment embedding, and token embedding. BERT learns and uses the positional embedding to express the position of words in a sentence. These are added to overcome the limitations of transformer, which unlike an RNN is not able to capture sequence, because I told transformers means It is RNN plus attention model. This is transformer. We are not using, CNN, not RNN, convolutional neural network plus attention model. So, this CNN is not having the, capacity to capture sequence. So that's why we are using the position embedding, segment embedding, but can also take sentence pairs as inputs for tasks. Token embedding, these are embeddings learned for the specific token from the word piece token vocabulary. BERT pre-training task. See, BERT is pre-trained using following two unsupervised prediction tasks. They are, masked language model and next sentence prediction. Masked language model. The masked language model randomly masks some of the tokens from the input, and the objective is to predict the original vocabulary ID of the masked word based only on its context. Unlike left to right language model pre-training, the MLM objective allows the representation to fuse the left and the right context, which allows us to pre-train a deep bidirectional transformer. Next sentence prediction. Generally, language models do not capture the relationship between consecutive sentences. BERT was pre-trained on this task as well. For language model pre-training, BERT uses pair of sentences as its training data. The selection of sentences for each pair is quite interesting. Now, I will show you the implementation for BERT. See, I am using the Google Colab to run the program. See, to get the Google Colab, you can type Google Colab. Sorry, let me connect to the Wi-Fi. 1 second. So, yeah, it's connected. Now we will reload the page. You can see collab.research.google.com. I have connected it. New notebook. We have explained in many videos. So you have this because it will give you 13 GB RAM, free RAM in this Google Colab. So we have to connect to the runtime. Change runtime type to GPU. So you have connected to GPU and you have saved it. Now connect. Then you will get a green arrow mark here once it is connected. Fine. So now I will get into the, this command. It is the pip install PyTorch transformers. We need this PyTorch transformers. I am running this command. So it is pip install PyTorch transformers. I think it's already done it. So it will do it. Yeah, requirement already satisfied because I have already done that. So this is we have done it. So we need a PyTorch transformers. Next, I am going to run the program. So we have to import the necessary libraries. I am importing that. I am importing. You can see here I have import torch from PyTorch transformers. We have imported BERT tokenizer, BERT model, and BERT for masked LM. We have imported those things. Then we are loading the pre-trained model tokenizer vocabulary by this piece of code. And after that, we are tokenizing the input. The text we are giving this is the text. You can see it here. See, who was Jim Henson? Jim Henson was a puppeteer. So this is the sentence we have given. This is the text. So just I am trying to execute. After that we are tokenizing. You know what is tokenizing from an NLP perspective. So I'm just running this piece of code. It's downloading the necessary libraries for BERT tokenizer from pre-trained, those things. It's done. After that, I am going to mask a token that we are going to predict it. That's what I am going to do. Just I am masking a token. That token I am going to predict. So that's what I am doing. So For that, uh, I am, again passing this code. Then I have this. Then I am running this. So what I'm doing here is I am mask a token that will try to predict back with, you know, by using BERT. So the mask index I have taken as 8, and the tokenized text, it is, we have taken as masks. For example, here, if you see, it's, the masked text, it is Henson, who was Jim Henson. So that only we are going to mask it. Let me execute this code. So we are defining the sentence A and B indices associated with first and second sentence as, we are converting the token to vocabulary indices by using this piece of code. Fine. Let me run this. Yeah, it's there is no error. After that, what we have to do is we have to convert inputs to the PyTorch tensors. For that, we are converting the inputs to the PyTorch tensors. So I'm running that piece of code. You can see here I am converting the inputs to the PyTorch tensors. After that, loading the pre-trained model. That's also model.evaluate. Then it will, display all the characteristics of the model as well. See, we can see it here. So that's done. You can see what are all the, BERT layer. See, everything it is mentioned here. So that's fine. It's done. Now, next thing, what we need to do is we need to put everything in CUDA. So that's what, even in the previous programs when we implemented transformer as well, we have done the same thing. So we are putting everything in the CUDA. See, this is what we need to do. Let me run this piece of code. The tokens tensor and to tokens underscore tensor to CUDA. After that, we have the segments underscore tensors and model dot to. So it is run. It's fine. I think it is running fine, and it is the model it is showing here. We can see here the BERT pooler, everything. It is the model. It's displaying. After that, what I'm going to do here, we need to predict the tokens by using the program. See, the next piece of code, I am trying to predict the token that is masked. See, predicted token is Henson because this is the one, it is masked. You can see it, here predicted token is Henson, right? If you see in the top, you can see it here. This Henson, the word Henson only, we masked it here. This is the text we have given. After that, the mask index is equal to 8. And, in the sentence, if you see here, this is Jim Henson, where you put the mask here after Jim. That is, this is the mask. So the Henson, it is masked. So that is the token, it is masked and it is predicted. So this is the, BERT, how we can predict of the tokens. So this is a implementation for BERT. You can understand this. This is what I explained. See here it is once again. Here it is Jim Henson. This is the text given. After Jim we have given the mask here. So that mask it is Henson. So that's why we have got it as Henson. That's all. Thanks for watching. Please like, share, and subscribe. Thanks a lot.